So today we're going to be talking about solving the system of a simple harmonic oscillator. Right now this is just a mass attached to a spring, and I've drawn it just a little bit beyond the equilibrium point to show that in the case where the spring is a little bit stretched, that there's going to be a force in the negative direction that's proportional to the position multiplied by it's the position multiplied by some constant k, which is the spring constant. So we have the force is equal to negative kx, and we also know that force is equal to mass times acceleration. So we can rewrite this as ma is equal to negative kx, and bringing everything to one side, ma plus kx equals 0. And we know that the acceleration is just the second derivative of position, so we'll replace that. And this is our simple oscillator equation. So actually I'm going to simplify this a little bit more. I'm going to divide out by m here, and you're left with x plus k over m times x equals 0. Okay, so I want to show you how to solve this with a complex exponential, which I think makes understanding this problem a lot easier, or it's a lot simpler to solve the complex exponential. The complex exponential is e to the j, and then inside the argument here you have omega t plus the phase. So this omega is the frequency, this t is time, and then you have some phase shift of the sinusoid. So we're going to plug this into this equation. We're going to say x equals this exponential, and well, we already know what x is, we can just plug that in there. The second derivative of x is just going to be j omega squared times the original function. And if we plug this all in, we end up with j omega squared plus k over m, I forgot the exponential, e to the j omega t plus phi times j omega squared plus k over m e to the j omega t plus phi is all equal to 0. So we have this common factor here, we can cross this out, and all we're left with is j squared is negative 1, and then you have omega squared plus k over m is equal to 0. So omega squared equals k over m, and that means that the frequency of the system is the square root of k over m. So the only two things that determine how fast this thing oscillates about this equilibrium point is k and the mass. So just as a little example, if well, an easy example, if you have k equals 1 and m equals 1, then this omega is going to be 1 radian per second.